So I'll hand it over to Fatemeh and Shiri.
Thank you. So I'm here to present our paper, TCG event or task condition generation based event extraction. This is a joint work with Tongtong, Yuanfang, and Reza Haffari from Monash University. So what is the event extraction task? Usually we extract very important information, structured information from unstructured data. So we focused on generation-based event extraction methods. As you can see from a sentence as an input, we can extract 3 events, which are like, we call them event types of attack, die, and injure. And each event type has multiple roles, and each role has an argument. So in many previous work, they have done different detection or classification. For example, for event type detection, event type classification, argument extraction, and argument classification for different roles. So the composition of the event extraction task make it a very complex task for the state-of-art method. But recently, generation-based model, especially sequence-to-sequence models, made the event extraction task like less complex and less require less annotation data, which I'll explain shortly. In one of the most recent papers, they have used an encoder-decoder pre-trained language model like T5 to take the input instance plus some manually designed prompt or template to generate events from those input instances. So for this type of extraction, we require templates for each event type. So there are unknown number of event types and different type of arguments as well. So they fill in templates by generating a sequence at the end and compare with the ground truth to train the fine-tune the model and using those prompts. In another work, they called it text-to-event. They also use the sequence-to-sequence model, but they constrain the generation by applying external knowledge, like event schemas are the external knowledge that they constrain the generation. So the model will learn, and it is limited to generate a sequence of event information. How they done that? Because this structure format needs to be linearized and convert this format to a sequence of tokens. Then the sequence-to-sequence model will be able to generate events from those input unstructured data. How they done it? They convert the tabular or structured data to a tree format. So each from the root, there are different event types because each input instance may have more than one event. So there are different event type, and each event type has different connection or branches of like the roles, and each role has arguments. So they linearize it in like brackets and for each event type, and each event type has its own structure in a linear format. So when we have the linear format of the events, so it's easy to use sequence-to-sequence model to train to generate events from the input instance. So what we were thinking of doing to improve and improve the previous models results and generate a more effective model for event extraction was adding or injecting the task conditioning prefix to pre-trained language model, which is a very challenging task because there are different type of conditioning pre-trained language model which we trained, we tried them, each of these methods, like one is by only fine-tuning large language model. The other one was adding adapters to each some layers of the pre-trained language model. And the third method, which was adding prefix, was more effective. And I explain why we chose this technique to inject the knowledge to the pre-trained language model. So this shows the high-level idea of our method, which shows only the decoder part. It takes the tokens of input instance and also information about event types, which might occur in our data set. And the representation of both are fed to a prefix generator model, and the prefix are injected to the decoder model, and decoder model can generate event types and required information for us. So basically, we take the event schema information to generate prefix and inject it to sequence model. Then model will extract those information more efficiently. Here is the architecture of our proposed method. So for the highlighted parts are the conditioning of encoder model. How we condition the encoder? So we take the event types in representation by like using BERT or any encoder model. So we have the presentation of event types, and we use a function like pooling average operator to create a knowledge of. So it's a vector which shows the knowledge of our event type in our model, and then we use this knowledge. We put it in. We use it as the input of prefix generator, which prefix generator are shown here. So this will provide those prefix for us, and those prefix are injected to the encoder part of the pre-trained language model. So pre-trained language model will get the input instance plus those prefixes, and then for the next part, we are generating prefix for the decoder part. So in this part, we believe that the presence of input, the event type information for decoder part also will improve the result of the generation by decoder. So we use the event type information and also the sequence length generated by the encoder, and we use the mechanism of cross attention to generate the representation of sequence length and event type for the event type presentation for the task. And then we use those two vectors, concatenate them, and we use a prefix generator again to generate prefix for the decoder part. And for the training our model, we minimize the negative likelihood of this loss function. So for the experiment part, we have different settings. We use ACE data set, which has been used in the community for many years. it contains the statistic of ACE data set are mentioned in the table. This ACE data set, each instance in the data set may have a single or multiple event in the instance. And we also use the RAMS data set, which is not like a sentence level. It contains 5 sentences or a paragraph in each instance, and they develop this data set in a way that each paragraph has only one event. So the event present in each instance has only single event. So the baseline that we used the in the past different event extraction model use different type of tokenization. So some of them use only token annotation, some of them use token annotation and also entity annotations. And what we use parallel text recording or just linearized format of event each event. So it doesn't require fine annotation, like fine-grained annotation or like entity annotation, token annotation. We just need to know what's the event type of each instance and what are the arguments. So very low level annotation is required for one of our baseline, which is text to event, and our model also. But we compare our performance with all these baseline. For the ACE data set, which is a sentence level event extraction, we outperform all the generation-based models, like all the models that they use T5-based, which is a sequence-to-sequence model. We all know that if we use a larger pre-trained language model, the results definitely are better. So some of those models have used the BERT-large model, like one IE model used BERT-large, but they use a very like heavily expensive data set for training or their model using token and entity annotation data set. We also conduct some experiments on RAMS data set, which our model TCG full version of our model will outperform our baseline, which is text to event model. And so for F1 score for both argument extraction and classification, trigger extraction and classification results. So we believe that that cross-attention mechanism for decoding part will improve our result for RAMS data set, which has longer length of input text data. So we also conduct some ablation study. We removed some components of proposed method to see how they are affect the final results. So you can see we can we can train our model without encoder conditioning, without decoder conditioning. If we remove both conditioning, so it's just like a simple fine-tuned model, or what if we remove the cross-attention mechanism for the decoder and also for our final model. We also tried different length of prefix. So prefix can have different length. So from 5 to 100, we tried different experiments, and we found out that until we increase the, so by increasing the number of, the length of a prefix, the model has more parameter and training, of course, is longer. But when we increase the prefix length until 20, the model, the argument classification and trigger classification will improve. But after that, the trigger classification is still increasing, but the argument classification will drop a little bit. So for that reason, we decide to just, for the trade-off between the efficiency of the model for the training and also having less parameter, we just choose to have 20 as the length of the prefix. That was my presentation. Thank you for attending this presentation. And if you have any question, I'm happy to answer.
So if the next presenter would come up and start getting set up while we're doing questions. So I think questions start. Maybe I'll start with one. So I was curious, this distinction between the high-level annotations and the token-level annotations.
Yeah.
Do you have thoughts on how your model could be extended to take advantage of the token-level annotation when it's available? Or on the flip side, if you took the text-level annotations and did sort of an approximate assignment to tokens and trained BERT on the data set, the second one, how well do you think that would do? Would it have any effectiveness, or would it still struggle?
So if I get to your question, like you mean if we use the fully annotated data set?
Yeah, so do you have ideas to extend your model to use that data when it's available? I realize that's beyond what you did now, but whether there's potential there to do even better if that data is available, the token level annotation.
Yeah, we haven't tried that, but I think it would be, yeah, a way to try it.
Other questions? Yes, I'll bring a mic.
Can you please show us the architecture again?
Yeah.
So when you are combining for the prefix, the knowledge from the templates, how do you combine these two sources, so the knowledge and the thing you have from the MLP?
For the decoding part or the encoding part?
From the encoder part.
Okay, so this part, so the input of prefix generation is just knowledge that we generated. So we have n Yuan types, and we use the average pooling operation function to generate this vector or a knowledge there. And then this one is the input of this multi-layer precision model. Yeah, yeah. And then here the generated key value and for different layers of the encoder is generated.
And these two information is like concatenated, and then that's the prefix?
Sorry?
This information from the multi-layer perceptor and from the knowledge key is just concatenated?
Yes.
Okay, thanks.
Okay, are there any online questions? Oh, there's one more over there.
So what happens if I want to add another type to this type of architecture?
Sorry?
So what if I want to add another type to the n type that you have?
So in the extension of this work, we try to run zero-shot event extraction for new types. So we have different strategy for the zero-shot setting. I think the new type can be added to the so we can remove or add event type to our this knowledge dynamically in the zero-shot setting. So that work is like maybe I cannot talk about the strategy now because we have submitted to the ACL this year. So we maybe I can have a chat with you later about the strategy for zero-shot.
Okay, so let's thank the speaker again, and then we'll